Hi guys, so this is going to be your video lecture slash tutorial for Thursday's class. Since I cannot be there with you, I would like to still try my best to get you the information. So I'm going to be taking you through a series of slides. You'll be listening, you'll be looking, and if I direct you to go somewhere else, take a look at something, you should do that as well. You will want to get your flame test lab packet, the blue one, out and have that handy before we proceed. So again, you'll need your blue flame test lab packet. In addition, since this is obviously a video lecture, you're going to want headphones and your Chromebook. You must already be on it if you are reading this. If you don't have headphones or a Chromebook, please look and listen on with a table mate and then make sure you tell them thank you for sharing. You do not need to take notes at all on this video lecture. I just want you tuned in and engaged. If I ask you to stop and watch something on YouTube, please stop and actually watch it. When you get to the flame test part, follow along where I ask you to in your own flame test lab packet. By the end of the lecture, you're going to be able to basically use the two new formulas that you saw in the pre-lab, and I'll teach you exactly what each variable represents, and then you're going to take that and apply it to your own flame test lab data and complete some calculations. So the first thing that you have the option of pausing and doing, which I would strongly recommend because it's kind of fun, is going up to the basket up front, the small white basket on my desk, and you can grab a little square of something called diffraction grating. This stuff works pretty much like a prism if you're familiar with prisms, in that it takes a white light and it splits it up into the various colors of the rainbow that white basically just has all combined. So if you want to pick up a piece of that grating and kind of walk around the room, definitely look up at the room lights, maybe go over to the window, look outside. You aren't supposed to look directly at the sun, but you should see little rainbows show up on either side of the grating. If you're looking at 8 lights, you're going to see a whole bunch of rainbows. And basically, if you think about it, this is a condensed version of the flame test lab. We saw all of the colors separated out in the flame test lab, and the diffraction grating shows you that white light has everything, the full range of colors from red all the way on until violet. When you finish with the diffraction grating, it is a little bit expensive, so I'd really appreciate it if you would pop that back into the basket on my desk. Pause if you need to go play with the diffraction grating. Now, we are familiar with several different models of the atom. Rutherford's model, we know he discovered a nucleus and that there are electrons around the outside. But what he didn't say anything about is where those electrons actually are. And we know now that it's the electrons that are responsible for the really cool behavior of chemicals. So I've got some pictures here to show you what I mean by really cool. The same kind of steel wool you guys worked with the other day in the lab, you didn't get it to ignite until you actually put it in flame. But it turns out if you put it in chlorine gas instead of a room gas mixture like we have in our classroom, it spontaneously ignites in that chlorine gas. Why? If we take a non-reactive gas like argon, this is a noble gas, and we pass electrical current through it, it glows. And it glows very specifically purple. Why? Why is it if we take a metal, such as potassium, group 1 metal, and we pop it in water, or we even let it just sit out in air, especially if that air is humid, it reacts spontaneously, like this, pink. Why? What it all comes down to is very similar to the reasons why things worked out the way they did in your flame test. Different atoms of different elements have differing numbers of electrons, and those electrons, when you excite them, which we did by putting them into the Bunsen burner, they start to bounce around, and based off the number that are present, they emit different colors of light. Each of our different colors of light carries a different energy. Something red, like lithium burns, is relatively low energy. And all the way on the other side of the rainbow would be something very high energy, like a violet. Keep in mind this is on a sliding scale, going all the way from violet to red or red to violet. So any of our in-between colors will fall somewhere in energy content between red and violet. You should pause right now and just take a look at which of these samples you burned in the lab as well. Confirm whether you got the correct sort of color, and then see if you can narrow down what the unknown was. There is one substance in this picture that you burned for your unknown as well, and you should see the same flame color for that unknown as you see in this picture. Now, going back to this image here should look familiar to you. White light splits into red, orange, yellow, green, blue, indigo, and violet, aka the rainbow, where red has a smaller frequency and a longer wavelength and therefore less energy compared to violet. The exact opposite statement can be made for violet as compared to red. I like to always put this in the context of something really practical that we've all seen. So I would like you guys to please pause this presentation, go on over to YouTube, and type in chemistry of fireworks. You're going to see this first video pop up here, the chemistry of fireworks, 6.5 minutes. Take 6.5 minutes, go ahead and watch the video, and then pop on over to the lecture again when you are finished. So now that you've watched the video, you can see, and I hope you do, from here on out when you're at a fireworks show, if something's burning red, turn to everybody around you, let them know, hey, I happen to know that's strontium. If something's burning blue, turn to everybody next to you, let them know, that's copper. And yeah, you might seem like a total dork, but it's pretty neat that you actually know how fireworks are made. You guys have perhaps seen some of the other types of radiation that exist before. When we do the flame test, we're focused on this very small chunk of all radiation called visible light. As humans, that's all we're capable of seeing. That's all our eyes can visualize. But there are other things out in the universe that exist, and many of them are very practical and applicable to human lives as well. If we start on this side of visible light, these are things that are higher frequency and higher energy than what we can see. Ultraviolet comes first, ultraviolet meaning just beyond violet. Now, ultraviolet, of course, comes from the sun, can potentially damage our tissues if we don't protect ourselves from it. And we're able to protect ourselves pretty easily using sunscreen or just by simply having clothing on. Ultraviolet light is interesting as well in that we actually need it for our survival. We need to be exposed to UV in order for our skin to make vitamin D. So it's a fine balance between too much and not enough UV light. X-rays are something that we as humans definitely utilize. We've definitely harnessed the power of X-ray to look, for example, at bone health. But if you've ever been to the dentist, and I hope you have, and you've gotten one of those checkup X-rays done, you had to put on a lead apron or a little like vest of sorts. And that was to protect you from the X-rays going beyond and getting into your tissues because they can actually mutate your DNA. Even scarier than that is something called a gamma ray. Gamma rays are one of the highest energy forms of radiation. We do not have materials that can really protect us from these. Think atomic bomb level radiation. They're definitely able to get into our DNA and tear things up and rearrange it and basically ruin our tissues, create cancerous growths, and so on and so forth. Now, to the less energetic side of visible light, a few things you might have heard of. Infrared gives us things such as thermal imagery, which I'll show you in just a second, exists just shy of red light. Microwaves, of course, they can float through our air. They're relatively large, relatively slow. We can also harness their power to warm up food. And then the largest type of wave is a radio wave. Radio waves are moving constantly all around in our atmosphere. Because they're so low energy, they don't pose any sort of harm to us, but we've obviously put them to our uses so that we can transmit sound across large areas. Now you'll notice that in addition to having all these different types, there's a few more pieces of information here that are important. Looking at the picture here gives you a good indication of what a large wavelength means, going from crest to crest or peak to peak. The larger that space is, the larger the wavelength of that wave. The higher frequency, meaning it's moving past you very quickly, something is, the smaller its wavelength is going to be. So wavelength and frequency have what's called an inverse relationship. Here's a couple of pictures you might find interesting.